Hello, my name is Matt Jacobius. I'm going over our transport exam. We have the H2O from 0 to 5 centimeters on the left side and D2O from 5 to 10 on the right. And we know the information of H2O has a molecular weight of 18 grams per mole, or 18 kilograms per kilomole, and 1,000 kilograms per meter cubed for density. And a D2O has 20 grams per mole, or 20 kilograms per kilomole, with 1,100 kilograms per meter cubed for the density. Okay, so our molar flux over here is going to be 2.78, and because it's a binary system, the H2O is going to be 2.7 in the right direction, and then D2O is going to be negative 2.7, therefore it's going to be into the left direction. And we know this because the molar flux is going to have to equal to 0. And with that, for number 1, we can answer how much the mass flux is going to be. So H2O, because we have the 2.78 moles per meter squared second times its molecular weight, we get 50.04 grams per meter squared second. We also do the same thing with D2O with a negative 2.8 multiplied by the 20, and we get the negative 55.6 grams per meter seconds. So next, we're going to be adding up the mass fluxes. So 50.04 negative 55.6 would give us negative 5.56 grams per meter second, which means that the D2O is going to be mostly into the left direction, and therefore the mass flux is going to be like that. Next, so now for problem 2, we're going to be using equation 1-27. So we have the driving force here equation with the mole fractions, molar diffusivities, concentration, and diffusivity of a liquid. And so to show off some numbers here, we have the yi and yj. Those are going to be equal to each other because after 0.01 seconds, not much diffusion has occurred. So theoretically, I believe it's 0.53 for one, 0.47 for the other at the membrane. However, that's after some molar diffusivity has occurred, but they're so close together, they're essentially 0.5. And again, we're going back to the point that the molar diffusivities are going to be equal to each other. I guess one's going to be negative and one's going to be positive, both going to be absolute values same. And our diffusivity down here is going to be 1e to the negative 9, which is going to be how well liquid, solids, or gases diffuse to another membrane. And in this case, because the liquid is going to be 1e to the negative 9. And in a fine concentration, we need to take the total moles of each side and put it into a concentration. So in water's case, we have 55,555, and in D2O's case, we have 55,000. And so if we were going to be doing the calculations, we're going to be taking these, adding them together to get an average, and we get 55,277. And due to this, it's extremely close to 55,000. So for ease of math, we decided to just leave it as is. So when we put these numbers in the 1-27, we have the 0.5 because both molar fractions are essentially going to be the same here. We have 2.78 because that's what the molar flux is. Again, we have the 0.5 because they're so close together after an intermediate step that not much has actually changed with the mole fraction. And we have the negative 2.78. Then here's the concentration. We have the 55,000 due to them being so similar, and for ease of a number of an estimation. And then we have the 1 to the e to the negative 9. And when we all simplify it out, we have 278 on the top, 5.5 e to the negative 5 on the bottom, therefore 50,000. And so 5 e to the 4, with that we know that the order of magnitude is going to be 4. Okay, for problem 3, we have our initial, intermediate, and final steps. The solid lines are going to be pure water, and then the dashed lines are going to be denatured water. So first, for our densities, at the initial point, we're going to be having water of pureness maybe leveled out, and then at 0.01 seconds, some diffusion has occurred. So it's going to sharply drop off and then be 0 on the D2O side. And it's going to be the same exact sign over here, where D2O is not going to be anywhere on the water side, but as it diffuses, it's going to increase sharply. And over here it's going to be 1100. That's because it's density. And over here it's going to be 1000. And then in the immediate step, after 60 seconds has passed, we see this graph has increased the slopes, so that way more of it can occur. So over here we have a little bit H2O. There's a large, more gradual curve, and then less H2O on the D2O side, and then same over here, D2O, gradual curve, H2O. And then again, those points are going to be 1000 and 1100. And then finally, when it's all been diffused, we have D2O with 550, and then H2O at 500. And this is because at all these points, they're going to be equal to each other, because we're assuming a 1-to-1 mixture, and therefore half of the density has to be composed of D2O and half of the density has to be composed of H2O. Next, for the second graphs, we have the concentration of D2O and H2O. And for H2O, what's going to happen is that the concentration is going to be 55,000 moles that we had earlier. It's going to go down to its halfway point around here at the 5 centimeter mark. It's going to be the same thing with D2O, where it's going to have its concentration of 50,000 moles, and then as it gets closer to the equilibrium, it's going to sharply drop down at the initial step. Intermediate, it's going to look similar to the mass density of D2O and H2O. Over here, we're going to have the initial moles of D2O at 55,555 for H2O. And then we're going to be going down at these more gradual curves relative to the last one. And then again, there's still going to be 0 on either side due to it not being diffused enough. And as it diffuses to infinity, the H2O and D2O are both going to be half of what their initial concentrations were, just because it's a mole fraction of 0.5 to 0.5. And so that would be 25 for D2O, and that would be a little bit above 25,000 for H2O. So the next graph we have is the molar diffusivity, and we have right here at 0, and as it gets closer to the boundary layer, it sharply increases to a maximum of 2.78, and it'll sharply decrease down again. And it's the same with D2O, except it's going to be in a negative position, where as you get closer to the boundary, it's going to be increasing sharply and then decreasing. And then it's going to be the same situation as the intermediary, except because there isn't that much of a driving force as the initial maximum, the curve's going to be like flatter, not as sharp. So H2O is going to be going up to a lesser value, and then D2O is going to be going to a shorter value. And then finally, as time has reached infinity, there's going to be no more driving forces, no more molar diffusivity, because it's going to be a 1-to-1 ratio now and perfectly mixed. Each D2O and H2O molar diffusivity is going to be 0. Finally, with the last problem, we have the mass transfer. And so, similar situation as before, we have negative mass transfer due to, on the first problem we found, when we added up these two mass fluxes, total mass flux was going to be negative. And so this is going to be 0 for both sides. And then as we reach that 0.5 mark, it's going to go to the negative 5.56 and then sharply drop back down. There's only going to be one line though, because it's going to be the net mass flux. Okay, and then next we have the intermediate step, where again, due to the driving forces not being as great, it's going to become flatter and not as sharp. So as we approach the boundary layer, it's still going to go up, or excuse me, down in this case. However, it's not going to be as sharp as before. And then as time reaches infinity, we're going to be reaching 0 because there's no more driving force, therefore no more materials being moved around.